All right, welcome back. We are going to move right ahead with how we can involve our molar masses and this understanding of what a mole is with various calculations. So these are going to get a little bit more complex. These are mostly going to be considered multi-step conversions. So you're going to see various parts being embedded into this. But if you know your dimensional analysis process well, you're going to do great. So the next factor we need to be aware of is we may have a compound and we're just interested in a specific element within that compound. Well, we know that compounds are made up of fixed proportions of elements. So because of that, say for copper 2 sulfate, we know that for every 1 mole of copper 2 sulfate, there has to be 4 moles of oxygen, in this case, atoms. Okay, there's that relationship to things that are equivalent to each other. So in this first example, it says determine the number of atoms of oxygen. So this is asking specifically about oxygen that are within 24 grams of our copper 2 sulfate. So one little thing here is this oxygen is within the copper 2 sulfate. So kind of push out the whole diatomic that you know about oxygen, because we're just talking about oxygen within this compound. So one little thing is because we're involving grams, keep in mind you're going to have to know the molar mass of our copper 2 sulfate. And our molar mass is 159.61 grams per mole. Okay, so I'm going to start with what I'm given, and we're going to really use the units to direct how we're going to go from grams to the number of atoms. And think about the fact that grams, we can use our molar mass to get to moles, and then we can use moles to get to the number of oxygen atoms. So over here, I'm going to start with my 24.0 grams, and this is where I really like labeling what everything is, where you have your copper 2 sulfate. Okay, the first thing I want to do is get that into moles. So we know that using the molar mass, that for every 159.61 grams of CuSO4, we get 1 mole of CuSO4. All right, I prefer here to transfer over to, while we're in moles, to switch to atoms of oxygen. So I'm going to say that for every 1 mole of CuSO4, I have 4 moles of oxygen atoms. Okay, so that's a relationship within that compound based on that fixed ratio. So now that I'm in moles of oxygen atoms, I can go to how many individual atoms I have, and that's using Avogadro's number. So for every 1 mole of oxygen atoms, I'm going to have 6.022 times 10 to the 23rd atoms of oxygen. Okay, and I can see here, just if you need to check your units, grams of our copper 2 sulfate will cross out, moles of copper 2 sulfate, moles of oxygen atoms, so I'm left with just single atoms of oxygen. So being very careful as you multiply across the top, divide by the bottom, and then also rounding to 3 sig figs based on my 24.0, you're going to get 3.62 times 10 to the 23rd atoms of oxygen that are within that 24 grams of the copper 2 sulfate. Okay, I actually want to jump down to the very bottom, so skip molar volume for a second. This is just a little chart that walks you through that type of calculation. And basically you can see that moles is what connects all of these. We'll talk about volume in a second, but if we have mass, we can use moles to get to like how much we have. Or I might be able to go from molecules using Avogadro's number to get to mass. So the idea is that moles allows us to connect all these different units that we're going to be working with in chemistry. So this is just another example similar to one above. This one says calculate the number of grams in a sample of ethanol, and it gives you the formula that contain this many number of atoms of just hydrogen within that compound. So we know that for grams are going to be involved. I do want to just give you the molar mass, which you can add up from the periodic table of our C2H6O, and that is 46.07 grams per mole for the compound. Okay, so we're going to start here with atoms of hydrogen. So I'm going to start with my 5.82 times 10 to the 23rd atoms of hydrogen. And remember again, this hydrogen, and I'm going to have to kind of slant this down a little bit. So I'm going to go in this direction just to fit it next to that picture. Hydrogen's within the compound, so we're not dealing with the diatomic element here because it's in the compound. I'm going to go from atoms to moles of hydrogen. So I'm going to use Avogadro's number, 6.022 times 10 to the 23rd atoms of hydrogen. That's equivalent to every 1 mole of hydrogen atoms. Okay, now this is where I'm going to use the relationship between the hydrogen atoms within every mole of ethanol. So if I have I'm going to put up here 1 mole of ethanol, C2H6O, that subscript of 6 there is going to tell me that I have 6 moles of hydrogen atoms. So if we check units, I've gone from the number of atoms to how many moles of hydrogen atoms. So if I were to stop here, I'd have my moles of ethanol, but I'm looking for grams. So in this very last part here, I'm then going to use the molar mass. So I have for every 1 mole of C2H6O, I'm going to have 46.07 grams of C2H6O. Okay, and you can see how those last set of units do cross out to leave us with grams. So when you plug this all in, that many atoms of hydrogen in a sample would be equivalent to 7.42 grams of my C2H6O. Okay, so you can see how I'm utilizing dimensional analysis, molar mass, the relationship of hydrogen in this ethanol compound in order to move pretty easily between the units. And it's just going to take some practice. We're going to be using this a lot this unit. One little fact that you should also be aware of if you go up a little bit to molar volume is we can use molar volume if we're dealing with a gas at STP. So 2 very important parts here in order to do this is when you have if we're going to use molar volume, this is the volume of 1 mole of a gas. It has to be a gas. It cannot be a liquid or solid, and it has to be at STP. So STP stands for standard temperature and pressure. So you can see the conditions there for temperature and pressure. So it has to be at those conditions. If we have 1 mole of a gas at STP, that is equivalent to exactly 22.4 liters of that gas. So just like any conversion factor where we have 2 things equivalent to each other, we can also use this in dimensional analysis involving, in this case, moles. So this just simply says what's the amount of space occupied by 1.75 moles of carbon dioxide gas at STP. So when I read this, I have to be aware that, again, I have my gas and it's at STP. So that would allow me to use moles to get to volume. So I would start with my 1.75 moles of CO2. Okay, I'm starting with moles, so I would have my 1 mole of CO2 would be equivalent to 22.4 liters of CO2. Okay, when you actually multiply those through and you keep your 3 sig figs that you started with, you would get 39.2 liters of CO2 gas at STP. Okay, all right, so you're going to practice this quite a bit because, again, it's going to be a pretty essential set of skills that you need to have down as we move forward.